Hello, my name is Brian Murphy, and for my machine learning project, I decided to try to predict subway ridership using MTA data. So, some of the objectives for this presentation are first, I'll go over the introduction and motivation for the problem. I'll go over my data set that I used, some analysis I did, and some pre-processing, how I selected a model, and how I trained the model, and finally, I'll conclude with some of my findings. The New York City subway operates hundreds of stations on a 24/7 basis. It is one of the only systems in the world that does so and is certainly one of the largest, if not the largest. As a result, there's lots of data potential here. I also work for New York City Transit in the MTA, and I wanted to know if ridership could be predicted using machine learning in any meaningful way. I also, as a New Yorker, wanted to see if my gut feelings of the subway system or when the best times to ride are correct. See if I can actually do a decent job of predicting that. The data set I decided to choose comes from the New York State Open Data Portal, data.ny.gov, and here is where the state publishes all of its free data sets for public use. So this is a whole catalog of information coming from everywhere. One of these data sets includes the MTA subway hourly ridership starting in February of 2022. So this is something that is constantly updated. It seems like it's updated at least once a day, if not every few days. And there are over, when I downloaded it at least, there was over 12 million records in there. The one thing to note with it, well, that I found out was that it's always at least 1 week behind, and it presents its data in time series format. So this was useful for when I actually chose my model. The dataset itself has in total of 12 columns. However, for my purposes, I focused on the transit timestamp, which has data in an hourly format, and as well as an AM and PM format, which was something I had to filter out. It also has the station complex ID, so R533, N060, etc. So those are just like unique identifiers for each individual complex, and the complex is actually the full station name. So that'll say something like Times Square on the 7NQRW or something like that. It also has the routes in there. So the routes like the 7, the NRW. And of course, since I wanted to predict ridership, I wanted to focus on the ridership. And finally, the payment method. So whether it was going to be coming from Omni or whether it was going to come from MetroCard. While that's not too important for the purposes of this model, it may be important just to try to predict how many riders there are. So I decided to try to focus on those few columns. Looking at the data, when I downloaded it, there were over 12 million rows of data spread across 425 station complexes, 93 routes, and based on some quick analysis, it looked like there was kind of a trend. You can see here that while there are some outliers looking at towards the beginning of the data set and maybe towards the middle in January, overall it seems to be kind of trending upward, and while it does oscillate up and down, I hoped that this was something that could be fit for a model such as linear regression. Looking at the data a little more granularly, you can see that there are some station complexes that have over 2,500 ridership and like over 1,000, whereas on the low end, there are some that have like 4 or 5 on average an hour. So this is just average hourly ridership within that specific station. Looking at it again in more detail, we can see that the average hourly ridership on the top end, while overall it's 155, on the top end it could go up to 2,800 depending on the station, which in the first one we have N060 Times Square, 42nd Street. That one has 2,900 almost. R238, Grand Central, 1,500, etc. In the middle, there looks like there's more of an 88, 89, so that kind of stays in the same realm. Whereas on the low end, it goes from 10 at Tompkinsville all the way to around 5 an hour at Broad Channel on the A and the S. And what this showed me during my analysis was that while the top and bottom averages, those can vary wildly, and here I've plotted some random stations from all three groups just to show that, individual stations seem to be somewhat stable, or at least on the low end they were kind of stable. So my thought was, again, maybe I could try to fit something to the individual stations first rather than trying to focus on the overall or go into the overall, compare the overall fit versus the individual station fit. Part of my pre-processing process of this data was to look at it, and I found two rows that had NAN as station complex, both of which out of the 12 million, so I simply dropped those. I also used get dummies to convert all of my columns that had alphanumeric data, like the routes, the station complex ID, and the payment types, into actual columns. So just so this way I could get everything to smooth out, and I could actually train my linear regression models on those. So I also dropped the columns that I didn't need, because when I didn't do this, then the data became far too large for my computer to handle. This included the georeference ID, latitude, longitude, the its UID, which is just the timestamp, and the ID wasn't really necessary because I already had both of those. The transfers, which was actually part of ridership as noted in the documentation for the data, the borough, the station, and the complex. The reason I dropped both of those was because the station complex ID has a one-to-one relationship between that and the station complex. And of course, the ridership I had to drop as the target. Because this was time series data, looking it up and doing my own research, I found that adding the year, the month, the day, and the hour was something that was ideal, so I decided to do so. My first consideration when selecting my model was that the knowledge that I was working with time series data forecasting. So this wasn't something that could be done with logistic regression. I wasn't trying to predict which station. So I decided to look up to models that could do forecasting. I also needed something that was quick to train and could actually run on my computer. And I needed something that could run on limited RAM. With some models, when I tried to like XGA boost or ADA boost, when I tried to run it, it was just asking for far too much RAM. And I also noted that, especially when I exploded out the columns, the alphanumeric columns, then it would be over 2.3 gigabytes. So it would ask for far more than I actually had access to. So those were some of my considerations when selecting my model. So this came down to really two options. The first one, of course, was linear regression. In previous assignments and my own experience, it's been relatively fast, allowing me to quickly train a model, go back, reprocess it, and then try it again. And it was something that could actually run on my system in a reasonable amount of time. Another model I looked at was Arima or Ceramax, which is a time standard for time series data modeling, and there was a Python module available for it. There were two other attempts that I tried, AdaBoost or at least I thought of. My AdaBoost classifier, it just did not have enough memory to, one, run in a reasonable time, and two, to run at all. Even when I was training on a subset of my data, it just took far too long to run, and I had to stop it after several hours. Logistic regression, of course, was rejected because it wasn't a classification problem. My methodology was to first sort the data set by data sending, as this was time series data, and research showed that I should do that, as well as also split it up based off of using time series split, which is one of the scikit-learn modules, rather than just using the standard train test split. I would then train the model on the last 6 months worth of data, from June 2023 to November 19th of 2023, and to train the model, I did two methods. The first one was to train it by month, which I theorized should have more noise and would most likely be less accurate and not be able to draw a good line, and as well as to train that by complex ID, which I theorized should be a little bit more stable. I used the built-in model.score feature in order to score my models, and I also plotted the differences between the prediction and the actual in both cases. So overall, I got very poor results when I used linear regression. The model score was 0.016, though I did find that the line fit better when it was trained by month instead of just by the station. So as you can see here, it was actually able to draw a line when I trained on all of the stations for the whole 6-month period. It got something at least. However, when I trained it by each station separately. I found that it did a much poorer overall. As you can see here, my predictions were far below that of my actual data, and it actually didn't seem to draw a line at all between the two. So it seemed that, contrary to my expectations, that training by all of the data was more stable than training by each individual station, and then combining all of those. Some explanations for how my models did was simply there could have been more time. Maybe I just needed to run different models for longer in order to try to get a better fit. I also most likely needed better features. So things like construction or events or maybe ball games, those are all things that affect ridership, and those aren't things that are captured in the data set. There also could have been some sort of technical malfunction, either at the station or on the train, that prevented people from being able to be read correctly. So, and those things, of course, affect ridership. More data could have also been loaded in. I only used the last 6 months worth of data because that's all I could load. As of right now, there are over 15 million rows on the Open Data portal, and there are 12 million that I loaded in as of 11/19/23. So I could have benefited from having more of that data in there. However, due to time constraints, that simply could not be done, and as well as hardware restraints. My next steps for this project are threefold. Number one, I plan on training on additional models because I think this is something that is rather interesting and fun to do. And to do so, I want to install additional RAM on my computer. So more RAM means I can load in more data and hopefully I can get better results. And I also plan to continue researching other data processing methods as well as other models that I could possibly try out. My overall findings are, for machine learning, New York City subway data would require a bit more information, but it's something that could certainly be tackled. I know there are other data sets that could have been combined, however, loading them in would be challenging them. Overall, though, it seems like loading all of your data at once, even if it's only over the course of 6 months, seems to be a lot more stable than loading it in chunks and trying to train based off of those. So, more data is, of course, better than less data. So, with that, thank you for listening and have a wonderful day.